from Oxford, who's going to talk about predictions while we moderate. Phil, thank you.
Thank you, Adrian, and thanks for the introduction from all the organisers for inviting me to give this talk. We are interested in doing absolute free energy calculations, which is probably slightly untrendy at the minute. Most people seem to be doing relative calculations because they're a little bit easier, I guess, and you get the benefit of cancellation of errors. So I'm going to walk you through a recent example that we've been looking at, which is to do with bromodomains. And just to sort of fill you in the picture a little bit, bromodomains are small protein molecules or domains that recognize acetylated lysines on histones. And that is part of the recognition process that controls transcription and things like that. And there are 61 bromodomains found in 46 human proteins. And they're of therapeutic potential generally in the case of cancer, but also in things like inflammation and viral infection as well. And this is what they kind of look like. They're a small sort of spore helix bundle. And you can see here there's a little pocket at the top, and this is where the histone comes in. This is what you recognize as the natural agonist, or natural binding partner, which is this acetylated lysine here. So this is a conserved fold across all the bromodomains. And this asparagine is key in recognizing the acetylated lysine. It's almost 100% conserved, not quite 100% conserved, but almost. And there's also, just going back to the previous speaker, there's also a nice conserved network of water molecules in the bottom of the pocket here as well, which have also received a lot of attention in the past in the context of drug design. And fortunately for us, it's quite a small protein. I say it's fortunately because that helps the sampling issue. And also, fortunately, it doesn't appear to move much as well, which is also rather handy for the sampling issue as well. So, in the case of it being a drug target, although a few of them have been very well characterized, the links between the pathology and individual bromodomains is still not clear in all cases. And so there's a desire generally to develop selective probes, even if you're not interested in developing actual drug molecules. The idea of getting selective probes is still useful. And we have lots of ITC data, isothermal titration calorimetry data, and crystal structures, mainly from the SGC, for both diverse series of compounds and for multiple proteins. And we wanted actually at the time, this goes back to how we kind of got interested in this, actually it's going back about 5 or 6 years ago, the SGC was rather interested in trying to understand better the ITC data per se, and to say, well, could you actually try and use that in a more prospective way, rather than using it what normally happens in a retrospective fashion. You get an odd result, perhaps in the free energy of binding, and then you go back and you say, oh, well, it's obviously this because there's a strong enthalpic contribution, or so on and so forth. So originally, this was kind of the driver for us, actually, was trying to understand the ITC data better. But we realized early on that, of course, to do that, you actually have to be able to predict the free energy better as well. And actually, in the case of absolute binding free energy calculations, which is what we were proposing to do because of those diverse molecules, it wasn't easy, it wasn't really obvious how you could do relative calculations between a diverse set of molecules, so we had to use absolutes. But as the field wasn't quite as mature, I'd say, as relative binding free energies, we really needed to make sure that we could validate this pretty well before we did anything more. And so that leads us on to sort of 3 test cases, which I'm going to walk you through, just to give you a flavor of actually where we think the state of the art, if you like, is with regards to absolute free energy calculations. So this is kind of like, essentially it's kind of benchmark, if you like. So the first case is this diverse ligands for BDR4. And this is the methodology that we're adopting. It's nothing particularly fancy, as it were, and you've seen most of these kinds of alchemical transformations before, so it's just a version of that, essentially. This is just how we're doing it. We're doing this all in GROMACS. These are the kinds of numbers of windows that we're employing, using Hamiltonian exchange. At the time, we were using GAF 1.5 for this first study, for the ligand parameterization, and the sort of, the overarching sort of guideline for us was to kind of follow the best practice as far as possible, because at this point in time there were several reports coming out of the literature about several little tweaks that you could do to maybe enhance the accuracy of certain things. So all we did was to basically say, well, let's just see how far you can get or how well you can do, just adopting what is currently best practice in the literature. So, yeah, so the first case is this diverse series of ligands against BRD41, which is one of the bromodomains. So this is the diverse set that we have. So you can see here these are very different compounds. So it's quite hard to imagine mapping between these different compounds in a relative free energy calculation scenario. And this is the crux of it. So I've shown this kind of data before, so I'm not going to talk too much on this, but this is the calculated versus the experimental. You can see here, this is pretty accurate. So of course this is slightly cheating because we knew the answer before we started in this case, but the mean absolute error is pretty impressive. It's down to 0.6. And you get quite a nice good correlation coefficients for this as well. And this is done with 3 peaks per calculation, just for Peter, so you can see. So, so you can see here these are genuine error bars, right? So we were rather keen to make sure that we did have a genuine estimate of the error in this case. But of course that was slightly artificial. In a real discovery scenario you wouldn't have all that luxury of knowing the crystal structures. So we went back and tried to dock or replicate a sort of docking scenario. So we docked all of the ligands back into the protein. And of course when you do docking you get lots of different solutions to that. That's why there's more solutions here than there are ligands. And the docking does a pretty good job, right? So, I mean, you can actually see that when you look at the docking results, everything is in the right place. So you get pretty good RMSDs. And even in the case where some of the RMSDs look a bit suspicious, the main interactions in the binding pocket are pretty well conserved, and all of this stuff is kind of flopping in the breeze anyway, so we weren't too worried about that. And it turns out that although you can, of course, get quite nice docking pose solutions, of course, you get fantastic correlations with the scoring function, and you've probably all seen something similar to that before. But when you then re-rank your sort of, or you calculate all of the solutions with the free energy approach, then you can actually recover some of that nice correlation again, and the error is pretty good still. It's not quite as good as I showed you for the crystal structure starting points, down at about 1 kcal per mole, but it's still pretty impressive. And what I wanted to sort of move on to talk most of today about was actually doing the other kind of question. So that was saying, here's a lot of different ligands binding to one particular protein, but there's another kind of question, which is basically if you have one ligand, can you say which protein it likes to bind to? Okay. So, in other words, multiple bromodomains in our case. Okay. So we have this compound called bromosporine, okay, which is a broad spectrum inhibitor of bromodomains. And lots of ITC data for this guy. And we also have, for 21 of these proteins, we also have a crystal structure in the apo form in the PDB. And now we've moved on to GAF 1.7, and I'll come on to talk a little bit about torsional reparameterization as well. So a nice spread of free energy of binding to different bromodomains here to explore. Of course, we don't know the binding pose, or we didn't know the binding pose. So again, this time we have to use docking to get the initial poses. And then we calculate the free energy, the absolute free energy for each of those individual poses, okay? And then the top 5 I'm showing you here. So this is our favorite one, if you like. This is the best binding, or the best binding pose, okay? And then we've got sort of potential candidates from the docking solution that score slightly worse, okay? And as we were doing this work, a crystal structure did actually appear, and we were holding our breath rather nervously, but actually, fortuitously for us, it's actually, we got the right answer, so that was good, right? So this is this is our best pose. This is number 1, compared with the crystal structure that came out. Okay, so this is this BRPF1 with bromosporine. Okay, so it's a pretty good overlay. The RMSD is about 2.3. So that gave us pretty good confidence that this approach was likely to be okay, and we could proceed just using the dock solutions that we'd evaluated from the early part of the study. So this is the upshot. This is calculated versus experimental. You can see here, this is not quite as nice, right? We're having trouble with this. This is a very much harder problem to solve. You can see here we're down at mean unsigned error of about 1.7 kcals per mole. Not so good on the correlation as well. So at this point, I presented some of this earlier last year to, maybe some of you have seen some of this before. And there were several suggestions from that discussion of things that we should be trying. So we tried RESP charges, so we're using AMC1 VCC charges. We tried RESP charges, that made things worse, that was bad. We tried a longer sampling in each of the windows, so instead of 10 we went up to 30, that made no difference. We started from the crystal structure now, where that was available, made no difference. We started from different end state starting structures. So what I mean by that is that in the series of windows you kind of you annihilate from, or you create from a certain position, and usually you just use that same one and move the windows along, as it were. But in this case, we tried to say, well, if you start from the apo state and equilibrate that a bit longer before you start the actual go into the lambda regime, perhaps you approach it from that direction, you should actually get a better equilibration, or a faster approach. You do get slight improvement, you do get faster equilibration or convergence of the windows, but it's not particularly improving the accuracy. So people suggested, oh, you might want to look at the torsions, because the GAF torsions are not that great, and in particular the sulfonamide torsion. So we did look at all the torsions, and the sulfonamide one is indeed pretty poor. This is just an example of this is the sulfonamide torsion, in fact. So you can see here, this is the high level of theory. This is the result you get. This is then GAF 1.7. You can see here the barriers are in the wrong place. Okay? So then we reparameterized that to give us new molecular mechanics parameters and put those in. And yeah, you get a slight improvement. So this is the result of that. Now you get a slightly better mean unspointed error, but a still pretty poor correlation. And actually, we couldn't really get much better than that. That's probably about the limit for this. So I think that probably, I'll come back to at the end what that might be. So that's one example where we tried to do one ligand, if you like, against different proteins. A second example is, well, it's kind of two ligands in this case, looking at the BET subfamily. So it's one small subfamily of these bromodomains. And this is the kind of subfamily here. So there's kind of two branches to this BET subfamily, so-called BD1, okay, and BD2. And there are two compounds of interest with respect to these bromodomains. One is this RVX208, okay, which is selective, okay, meaning that it binds slightly better to BD2. Okay, so this is the data here. So it binds slightly better to BD2 than compared to BD1. But this RVXOH compound is non-selective. Okay, you don't get any selectivity. Okay, and the difference between these two molecules, if you look, is just here. This is an OH, and this has this ethoxy hydroxyl group here. Okay, so it's quite a small subtle difference. Okay, and this guy is, as I said, non-selective. So, can we actually recover that using absolute free energy calculations? Is the question. Okay? Now, there's a slight twist to this, because actually, if you look at how these compounds bind in the binding site. The 208 compound, this is the selective guy, okay? He binds, yeah, in the same orientation, okay? That's what you would expect, right? But the RVOH compound, okay, this one binds in a different orientation, okay? And this is something that sometimes people take for granted, especially when doing the relative free energy regimes, is that you have the same binding mode between the regimes, okay? And you would have probably have missed this if you had adopted that kind of approach here. So this is kind of intriguing. Now, it turns out that this, the ethoxy group that's on this guy cannot actually bind in this pose. Okay? So that's the reason why you get a slight difference between these. So that's kind of intriguing. The good news is that when you do the absolute binding free energy calculations, you actually recover the right pose. Okay? So the calculations do actually say that this guy is a better binder in this orientation compared to this possible orientation for BD1. Okay? So it's all consistent. It's all really nice. So these are the predicted affinities, okay? So we can recover that quite nicely. So the 208 compound, we can see generally binds to BD2 compounds, pretty much with a much better, as it were, than the BD1 compounds at a significant level, with this p-value here of 0.03. And when we look at the RVOX OH compounds, then we see that actually that selectivity has kind of disappeared, actually reproducing exactly what you see experimentally, which is kind of nice. So no significant difference between these two different types of bromidome. Okay. So that was kind of a really nice result, and this is putting it in the same kind of plots that I've showed you before. So calculated versus experimental. You can see here now we're down at a very good mean absolute error again, 0.8 kcal per mole, really quite nice, reasonable correlation coefficients. So again, we're actually doing quite well with these absolute calculations in this sense. So I hope I've sort of managed to convince you in this sort of brief talk that we're able to identify the crystallographic pose from a set of possible poses, which is quite important when you don't actually know that answer up front, okay? And you can do quite a good job, quite accurate, so RMS errors of 1 to 2 kcals of predicting the affinities of ligands with diverse scaffolds, okay? And we can predict selectivity well for one case, the RVX compounds, but perhaps not so well for this bromosporine compound. And that suggests to us that ligand parameters are still problematic. We think all the things we tried, and what's not an exhaustive list, and welcome more suggestions to try, but it seems that somewhere those ligand parameters are still a little bit problematic. But even worse than that, identifying the source of these errors is non-trivial. We had a little bit of a discussion about this yesterday, but I think even for these kinds of problems, identifying exactly where the source of the error is kind of tricky, okay? And ultimately, relating affinity back to the protein structures is actually still difficult. Although you can say, yeah, this one does better than this one, and so on and so forth. Actually, the reasons why, we still don't really actually have a good way of doing that, I would say. Okay? Perhaps we might hear something about that in the next talk. Maybe, no, maybe not. And I'd say also it's important for us as a free energy community to have kind of markers in the sand. Okay, so what I mean by that is kind of data where this is kind of where we are at this point in time, and you know, this is what you should be aiming at. So if you've got a method that you think is better or faster or more accurate, then you know, you have something that you can aim at and say, this is where we are, this is the same data. And to that extent, we've tried to be very open about the data set. So the complete input files from the first study in the chemical science paper are available on Zenodo, so anybody can download the input files, okay? The complete input files again for the JAX paper, which had the bromosporine and the RVX study, are available on JAX as supplementary information. Matteo also did all of this work, I should add, did a nice tutorial on Gromax, using Gromax 16 at the alchemistry.org website. And I'll just end with this quote, this quote, which was on Derek Lowe's blog last in February when the paper came out. So we're getting quite close, but maybe not close enough for some additional chemists. Okay. But with that, I will end, and I will actually thank Matteo, because Matteo did all of the work and deserves all of the praise. He sat over there somewhere. There he is. And so all the praise. He's now postdoc with Bert de Groot. I'll thank Stefan at the SGC and the guys at Unitech and these guys for computer time, and you guys for listening. Thanks.
Thank you. Now, before I ask for questions, one of the really nice things that we've noticed at this Finding Free Energy workshop is the large number of more junior investigators and people who are coming into the field. So I would like to pick on you and ask for questions from the floor. So if you could arbitrarily divide yourselves into those of a certain age, you can sit back. And those who are under that certain age, could we take some questions from some of our students and our postdocs, please? Don't be shy, please, thank you.
So most people here seem to talk about good finding partners, and I've done some work on absolute finding free energies as well, and most of the problems I see involve bad finding products. Have you actually tried that with you know, anything that you expect to have a finding free energy?
You mean like essentially a negative control, essentially. But I don't think we've looked at that in a systematic way, and that would be a good thing, certainly, to do. You're absolutely right. Yeah, and that's not done enough of in the literature as well. Sort of saying, well, here's something we know is not going to work. But I guess the trouble has always been trying to get the right result for stuff you know should work. But you're absolutely right. We should do more of that kind of negative control as well. Yeah, that's a good point.
Okay, so the results you showed, those were obtained with Gromax 2016 as well, or was it pre-506?
The earlier stuff was done with earlier versions of Gromax.
With previous 506?
Yeah, 504, yeah.
Okay, but so the question is, you've shown a double decoupling method there. You talked about annihilation as well. Yeah. And keeping to best practices, or I guess I could also point that one too, I guess. But have you done actual double decoupling method here with brittle bond algorithms, or have you done the approximate one?
It's we didn't do virtual.
No, so the charges are annihilated, but the van der Waals decoupled, so the internal interactions between the van der Waals reactions of the ligand, there are, but the charges are just go to zero. Okay. And this is because, like, in the older version of Gromax, it was a bit trickier to set up the system that way, so you need to play with topology quite a bit to make it
Yeah,
work.
well, from 5 or 6 you could actually do it.
Exactly, yeah, but this was all done before.
Yeah.
Okay, well, thank you very much, Bill. I'd like to invite our last speaker, Alex Heifetz from Evotech, who is going to be talking about the accurate assessment of protein-ligand interaction energy, achievable in seconds with a QM.
Okay. Thank you very much for the organizing, for inviting me, and for this opportunity to talk with you guys. And I'll start with a story, just to convince you that what we do is useful for drug discovery and why we do that. So I'll tell you the story of a drug for insomnia. Well, it's midday insomnia drug. So developed by Merck. And Merck make a lot of effort. This is a new drug for insomnia, came a couple of years ago. And what I wanted, the message, the key message of what I was going to say, that if you don't have a method that will help you to understand the interaction between the protein and the ligand, you will do a lot of effort to optimize your compound. And if you look on the publications on the development of this drug by Merck, you can see a lot of effort. And this is only part of the publications. So if you look on the, and well, they work on this. They use GPCRs. They used modeling of GPCRs. They looked on the interactions, and recently there's about a year and a half ago, there's a crystal structure of their compound came out, and when we looked on this on the interaction, we couldn't understand anything. Because if you look on the compound, on the binding affinities, it's a super glue compound. It's 0.554 nanomolar compound. You would expect, if you look on the structure, if you do visual inspection or force fields analysis, you will see maybe about one hydrogen bond, something hydrophobic, interaction via water molecule. That's all, like 3 interactions. You don't understand what's going on here. Why this compound is so potent, from where the potency is coming. And I hope by the end of the presentation I will be able to explain this. But before that, I'll do some intro. The method that we're using to do QM calculations, and we're doing in industry, so industry is time is money, so it needs to be quick. You can't wait months to get the answer. You need something very quick. So you can't do usual QM calculations because it will take months. So what we do is other method called for FMO, fragment molecular orbitals. What we take the system, we break it into the fragments. For instance, each residue can be represented by the fragment. Ligand is also a fragment. The ligand itself can be broken into fragments if you want to understand more specific the interactions. And then we may perform the calculation. This allows to decrease the dimensionality of the problem from n in power of 3 to n power of 1, and this is actually what is adding a speed into that. This method is also parallelized, and which adding an additional speed to that. So, but it's still not very quick relatively, but it takes a couple of hours per system. For about 32 CPUs, it will take about 2 hours to calculate protein-ligand interaction per system. So what you get actually, what type of information you will see with that? You will receive interaction energy between your ligand or between actually every fragment with every fragment. When we are more interested, obviously, interaction between the ligand and the protein. The interaction energy is broken actually into 4 terms, which one of them is electrostatics, which interaction between charge residues. between charged particles and charge transfer is interaction between occupied and non-occupied orbitals. Exchange repulsion, which is a repulsion between two occupied orbitals, and dispersion is in forces between multiples or polarization that are caused between two neighboring molecules. And so you get, and what you calculate, you calculated the final, the total energy, which is sum of those four terms. So what you receive in the end is the list of interactions, but not only that, you will also receive what type of interactions, which, for instance, dispersion is more hydrophobic thing, electrostatic is more, well, electrostatical in nature, is attraction or repulsion. And this is something very more intuitive for the chemists when they coming to perform modification of their molecules. We done we performed some calculation on 18 of crystal structure of GPCR just to see what we get. We wanted to show in this paper, there was two papers that I'm going to, actually three papers that I'm going to speak today about them very briefly. One of them, we wanted to show that even if you have crystal structure in hand, you need a tool to understand what this structure is telling you. There is much more. You need a microscope to look on those interactions, and those FMO is this type of this tool. Otherwise, all what we count on mainly on our eyes, which can deceive us, or not, or tell us, or only partial part of the story. And I will go into in a second back to suvorexant to show you what actually we see there. So this was published in 2016. This was work we done with Matteo and Phil and other colleagues from Evotech. And if we go back to suvorexant, we'll take the crystal structure of suvorexant, of this mer compound. You actually see that you have 10 interactions. With 10 interactions, you can explain why the compound is in sub-nanomolar range. But only if you look on this, you don't see those interactions. This is the list of interactions, yeah? This is the residues. Here on this plot, you actually see the breakage, the pieda of these interactions. So you can see that obviously yellow here is electrostatic term, there's obviously it's present, but you can see also blue dispersion term, which is hydrophobic, and you see there is a lot of hydrophobicity here. So there is very hard to detect hydrophobic interactions. On the other hand, as you can see, they are playing quite critical role. We perform also a correlation. We took SAR from 4 different structures where we have experimental affinity, and we calculated the correlation between the experimental affinity and the FMO calculated energy, and we see quite good correlation. We don't expect perfect correlation because what FMO is calculating is enthalpy mainly, the interaction, and ignoring the entropy, which is other story, which is very important, but is not part of the FMO. When we looked also on the distribution between different energy terms for 18 GPCR ligand crystal structure, we notice that electrostatics is about 43%, and hydrophobic is also about 40%. So we see that the huge role of hydrophobic in binding, which cannot be detected by eye. Cannot be detected by eye. You can guess that you have hydrophobic interaction, but you don't sure about this, and you definitely don't know how strong this interaction is. And this is like we are, until without FMO, you optimizing your ligand with one eye is closed, which was half of the story you don't see. You don't see this also when you do crystal structures, when you are analyzing crystal structures. So FMO allows you to open, or QM allows you to open both sides and look on this to have a full picture. This is also a case when we use FMO to develop drugs against asthma for kinase ITK. It was project together with Genentech. Just wanted to bring you an example here. When we use FMO in prospective way as a real drug discovery project. So we started with the HTS heat compound that was 460 nanomolar compound. When we perform FMO, you can see there is a residues in the binding site, but there is no interaction with them. So obviously this is example how you can use FMO as in prospective way in design of compounds. You look, you see what interactions you have, how strong those interactions. When you have, sometimes you have repulsion. To make compounds stronger binding, you should not only adding interaction, but you should remove repulsion, which is also very useful. In this case, we looked, there's a residues that we are not interacting, they are neighboring. And you might think that they are interacting, but you don't. And then we finish with compound that was 4.1 nanomolar compounds when those interactions was present. And you can see that the type of this interaction was mainly hydrophobic, because you see a large hydrophobic term here. This is actually also a kind of perspective. You don't use FMO mainly for predicting affinity because you need a range to predict affinity. And to build QCR, you need already strong binders. And when you have already strong binders, you don't need to do any more optimization. So it's always retrospective analysis. But just to show that FMO do work, if you want to predict affinity, this was in the project when we use this, and you can see from 2 series of compounds. We work on 3 series actually. This is for 2 series. You can see here quite strong correlation between the binding energy and measured potencies. This is additional examples for other series that we work on, that you can not only take compounds for 460 compounds and bring it to nanomolar range, but you can do also lead optimization manner when you have already strong compounds, and you can still continue optimizing it by comparing not only where missing compounds, but also missing interaction, but also where interaction can be made stronger. So it gives you not only the fact that I'm interacting with this particular residue, but it also gives you information how strong you are interacting with this residue, and maybe you wish to make it stronger. And this is the example when we have started with 4 nanomolar, finished with 0.17. Okay, but until now the problem with the FMO was it required high resolution structure. So if you're working on project, it requires that at least one crystal structure you will have. And then you can dock and do other stuff. But usually this is a luxury. In the project you don't have usually crystal structure. You work on for your particular ligand of interest. Usually do homology modeling, you do docking, and then where the QM most methods fails, including FMO. So what we wanted very quick FMO. We wanted FMO that we can use in kind of way like we use minimization tools or even MD. Something that can be very quick, in seconds. And recently we developed a method, actually we combine it with other method, DFTB. The method was recently, we published this, how it works, all the theory behind it. And this was just accepted by Journal of Computational Chemistry. And just if you compare the speed of that, this is if you use MP2 level of theory, MP2 method, then for different, this is for instance, this is for this sovorexon that I talked about. It will take you about 19,000 seconds to calculate. When you do it with FMO DFTB, you get the answer in 12 seconds. So the speed factor on average is about 1,000, more than 1,004 quicker. That's mean that you can start to use QM not only as an analysis tool, but you can use it as a tool to optimize. There is a few attempts was made to try to involve DFTB, to use DFTB in MD simulations. So this way you don't need force fields, or at least we hope you will not need force fields. Maybe because you calculate those parameters on fly from the system itself, from the change of the system. And this is something completely new, I think, and give us hope that all these MD methods we can be much more accurate. Again, we calculated with the experimental. There is using FMO DFTB, we see more or less the same result that we used with slow FMO. With FMO MP2, with DFTB we get also high resolution. And we also see that if you correlate slow FMO with the quick FMO, you also have high speed. But I want to emphasize, DFTB is a different method than MP2. It's not light MP2, it's different. So the conclusions, we have demonstrated that FMO is quick. It provides a list of interactions. This information is used in case of Evostake in industry, used to design new molecules, helps chemists. It's significantly decreased the effort and cost, synthetic cost. FMO, the quick FMO, provide the same level of accuracy like a slow FMO. And it's opened a new avenue that we started to work now to use FMO, to use QM methods as a modeling tools, as a tools to minimize structures, to optimize them, and in other like virtual screening, score molecules, because you have this increase in speed. I would like to acknowledge to Dmitry Fedorov, who develop FMO, who collaborate with us, to my Evotech colleagues, to Andrea, that I'm collaborating now, to my Genentech colleagues, and obviously Combiomed, BBRCC, to support this. And I want to also to say thank you very much for my former collaboration, Matteo and Philip, that we work very nice together, and thank you. And to you.
Do you have questions for Alex before we break for lunch? Yes?
Can we easily include the dissolution free energies, because normally it's done in the implicit solvent anyway. So with your
we include, and with DFTB we include the dissolution term.
And it helps.
Sorry?
It helps with overall comparison to whatever data you can.
I'll be honest, we didn't test it enough. To the system that we done to the system that we done it, it's give the same results. But the number's more realistic, let's say.
Yeah, in the example you showed where you were saying you could actually use it for design, in reality, to me, it looked like what you did is just pick up two reactions that weren't, or interactions that weren't present in the initial ligand. That was something that could be done by eye. So, how easy is it in reality to actually optimize on all these full parameters that you get out of the actual FMI?
Well, first of all, I think the FMO in reality is used. There is a lot of non-classical interactions or hydrophobic interactions that's very hard to detect by eye. We can look on them and say, well, this chlorine is near this OH and maybe they interact, but you're not sure actually. Better to have some tool that will provide you. Kerf suvorexant, there, if you look, you can guess. Yeah, you have hydrophobic C and hydrophobic C. Maybe they interact, maybe not. How strong this interaction is. The strength of the interaction is very, very important. To be honest, what the breakage into what type of interactions is less helpful. What helps you is a list of interaction and how strong you are. This helps a lot.
And just beneath the side chains of the protein ligand bias, are they flexible or is it static in this method?
Until now we use static,
Okay.
because if you optimize it with force field, it's not accurate enough in QM. So now what we do, you can optimize it with FMO DFTB. You use QM to optimize and calculate it. So it's not only just post factum analyzer, it's part of it. So this was the problem of this, why we couldn't use it widely. We use it mainly for kinases, where you have initial crystal structure. For your series, you have at least one crystal structure. Then it was very useful.
We take one final question and ask if we could continue this discussion over lunch, please.
When you split your protein into fragments and compute your molecular orbits, how do you treat the surroundings? Do you do that in vacuum, or do you include the surrounding protein?
You include the surrounding protein too.
How?
You calculate the interaction also between fragments. You're trying to compensate the fact that you break into the fragments. This compensation factor is included. The fact that you don't have the peptide bond, and you take all this into, and FMO is, there's FMO1, FMO2 to FMO3. You can increase the level and take it more into consideration. Fact that you have polarization of surrounding residues and everything, but this obviously you pay more. So it depends what you want to do. On the pragmatical side, if you want to calculation between protein and ligand, you don't need this. But if you want to explore how the structure, overall structure, then you need to take all these effects into account.
Okay, I'm going to ask us to stop here. We can continue this discussion over lunch. I'd like to thank all of the speakers in this session for very entertaining and engaging talks. Thank you very much.